Good morning, and it's a pleasure to see such a good attendance. So my job is more or less to give an introductory talk on radiological terrorism in general. What is I'm not going to assume anything about your knowledge of radiation, so apologies to those who are experts, of which I see many in the audience, but I'm going to try and go pretty slow. And let me just paint a scenario before we really get going, which I think is quite informative. And this was an incident in Goiânia in Brazil in 1987. Goiânia is actually a city very much similar to Manhattan in size, and you see it's got lots of tall buildings also. And has a population pretty similar to Manhattan. And in the late 1980s, they had a hospital, or a clinic rather, which had a radiotherapy component, which got abandoned. And amazingly enough, the radioactive source, the cesium source, was just left there, left in this abandoned building. And of course, ultimately, the radioactive sources were stolen, broken open, and...
I'll give you another mic, because you're not using that one over there, so...
okay.
And if you can clip that onto your belt.
Okay.
Put it in your pocket.
Okay, I'm doubly mic'd up now. Can people hear me at the back okay? Yeah, so these radioactive sources were stolen, broken open, and they glowed in the dark, and kids were playing with them, and they got sold and dispersed. And ultimately, when this came to light, when people started coming into clinics with skin burns, it became apparent what happened. And this is essentially what happened. That about 10% of the population of Goiânia, about 130,000 people, came to either emergency rooms or temporary screening locations to be screened, because naturally enough they were concerned about their radiation exposure. The results, in fact, were a very small number, a fraction of a percent, were contaminated, and a very, very small number, about 20, actually required treatment. And that's probably the most likely, well, it is the most likely scenario for any radiological terrorist event, that there's going to be an awful lot of people who are concerned and an extremely small number of people who actually require attention. So this scenario is something I think we need to bear in mind throughout the course of today, that really were most scenarios that you could possibly dream up, there's going to be very small numbers of people actually requiring treatment, but very large numbers of people who are concerned, panicked, worried. So what I'd like to cover in the next hour, or a little less, I hope, what is radioactivity, what is radiation. I'll talk about some different radiation threat scenarios, talk about how one might respond, ask the million-dollar question, will it happen? And then give you some clues to further resources. So we're about 100 years into the radiation era, if you will. X-rays were discovered in 1895 by Röntgen, and radioactivity was discovered the following year by Becquerel. And this is Marie Curie, who, as of course you all know, was intimately concerned with the early developments. The word got out quickly to, this all happened in Europe, of course, but New York City was quickly into the game. This was the tabloid at the time in 1896, the New York Morning Journal. And being journalists, they got their story exactly right. The College of Physicians and Surgeons, which is what is now here, is using X-rays to reflect diagrams directly onto the students' brains, making a more enduring impression than the normal method of learning. So above your heads, we're all wired up here. So what is radioactivity? Well, It's the spontaneous emission of energy, radiations, alpha rays, beta rays, gamma rays, which I'll talk about in a moment, from radioactive materials. And here is Marie Curie again with her husband Pierre Curie. So the three types of radiations that we have to worry about in this context are alpha, beta, and gamma rays. So let me just talk about what they actually are. Here's an alpha particle, and if you remember your high school physics, what is an atom? It's a nucleus with electrons orbiting around. Well, an alpha particle is actually a helium nucleus without the electrons orbiting around. It's just the nucleus of a helium atom. So it's actually a little cluster of 2 protons and 2 neutrons. And what goes on in radioactive emission is that this is spontaneously kicked out of the nucleus, out of a radioactive nucleus. So this is the nucleus, and it has 2 less protons and 2 less neutrons, and this particle gets kicked out. And that's an alpha particle. A beta particle, beta emission, also the same story, that a particle is spontaneously kicked out of the nucleus, in this case a beta particle, which is nothing more or less than a regular old electron, the same electrons that make electricity in wires. In fact, another particle is kicked out at the same time, in this case an antineutrino, not something we need to worry about. We're being bathed, in fact, with neutrinos and antineutrinos right now, but because they have no charge, very little mass, no spin, they don't actually interact with us, so they just pass straight through us. So it's the beta particle that we need to be concerned about. And in fact, they come in 2 flavors. This is the negatively charged beta particle, just the regular old electron. There is also a positive beta particle, the antiparticle of the negative beta particle, which can also be emitted. Antimatter doesn't stay very long in this part of the universe, which is basically matter. So an antiparticle, a positive electron, will meet up with a negative electron, of which, of course, we're surrounded, and will interact and make 2 gamma rays, which is going to be our next radiation. I'm fine, I'm good. And the gamma ray is actually slightly different from the alpha ray and the beta ray, but the alpha particle and the beta particle, by their names, can be thought of really as mini billiard balls, as little particles, whereas a gamma ray is considered more like a wave. You probably know from 20th century physics that, in fact, waves and particles are actually the same thing. They're aspects of the same thing. But it's much easier to think of gamma rays as part of a family of waves, starting off with radio waves, microwaves, visible, ultraviolet, X-ray, gamma ray. They're all basically the same thing. The only difference between them is the amount of energy they carry. And the gamma rays and X-rays carry the most energy. And as we'll see, that's why we're concerned about them. But other than that, they're basically the same things as radio waves and ultraviolet, infrared. But what makes gamma rays, as well as beta particles and alpha particles, special is the fact that they can do this process called ionization. So what is that? Well, here's an artist's impression of an atom. Here's a nucleus, and here's electrons orbiting around. And here's an alpha particle, or a beta particle, or a gamma ray coming along, left to right. And what it can do, what these particles can do uniquely, is actually knock orbiting electrons out of an atom. And that process is called ionization. And what's left with this atom minus an electron is called an ion. So what's happened is you've disturbed the structure of this atom. And if this atom happens to be in a molecule, which happens to be in, shall we say, DNA, it can disturb and break bonds, disturb the structure of that DNA. Now these 3 radiations are unique in having enough energy to be able to do that. A ultraviolet ray, for example, simply doesn't have enough energy to rip an electron which is bound to this atom to rip it out of that atom. Only the alpha rays, beta rays, and gamma rays can do that. And that's why they are biologically by far the most relevant radiations that we deal with. So they're biologically a lot more hazardous simply because they can ionize. So they're called the ionizing radiations for that reason. These three types of radiations, alpha, beta, and gamma, have very different properties, in fact, which turn out to be relevant to us. And the big difference between them is range, how far they can travel through material. Alpha particles, in fact, have a very, very limited range. They can go very, very short distances, microns, micrometers, in fact. So they can't, for example, penetrate a piece of paper. So they certainly, for example, couldn't penetrate your skin. So when we have a radioactive material which gives out alpha particles, we're only concerned about internal exposure. In other words, breathing in the radioactive materials, and the alpha particles are emitted internally, because externally they can't penetrate your skin, so there isn't a problem. Beta particles are intermediate. They can certainly penetrate a piece of paper. They can't penetrate, for example, your hand. So that's the sort of range that we're talking about with a beta particle. And a gamma ray, by contrast, is highly penetrating. You need large amounts of material. You need chunks of concrete or lead or shielding material to block gamma rays. So they're very different in terms of their range, and that really affects how they're going to affect you or I. So let me make this distinction, but really as we go, between external exposure and contamination. I mean, basically, after any sort of event, there are really two sources of irradiation that you might think of. External exposure, so there's some radioactive material out on the ground or in the air or something like that, or contamination, which means that the radioactive material is either on my body or in my body. So you can either be externally exposed or you can be contaminated, or of course both. Which leads me to the major pathways from a radiological event. So let us suppose there is some sort of release of radioactive material into the environment over here. So how is that going to actually end up impinging on us? Well, there's a variety of different pathways where that might happen. So now we imagine there is some radioactive material in the atmosphere here. Well, it can deposit. It can hit the ground. It can fall to the ground. And then you have radioactive radiation coming from the ground, which is often called ground shine. So radioactive material hits the ground, and then radiation is emitted. Or the deposition can be on you. It can fall on your head or on your skin or on your clothes, and you can be exposed that way. Or you can inhale the radioactive material which is in the atmosphere directly. Or you can be exposed directly from radiation from the radioactive material in the environment, and not inhaling it, but just external exposure. Or material can hit the ground, can start to be blown away from the ground, and then you inhale that. So there's a whole variety of different pathways, and which is the most important is very dependent on the very different scenarios that we'll talk about later. Broadly speaking, ground shine and inhalation are the two big ones. Either you get exposed because the radioactive material has hit the ground and you're being exposed from the ground, or you actually inhale the radioactive material directly. Those are the two main ones, but in different scenarios, one can be more important than the other, or these other ones can be important too. Now, external contamination is actually the easiest to deal with in many ways. Now we're talking about some radioactive material which has fallen from the sky onto your person, either onto your skin or onto your clothes. And in fact, the logical way to deal with that is to remove the clothing. And in fact, most radioactive contamination can be removed simply by changing clothes. And as you might imagine, internal contamination is a lot more problematic. If you inhale some radioactive materials, there's no obvious way of washing it out, as we'll see. So I'm going to be talking fairly quantitatively as we go along, so it's important to think for a moment about units of radiation dose, radiation exposure. And the standard unit is called the gray, which is actually an energy per unit mass, amount of energy deposited per unit mass of the material. More likely in our scenarios, it's milligray, thousandths of grays. There's a quantity called the equivalent dose, and that basically takes into account the fact that different radiations have different biological effectivenesses. So millisieverts basically takes that into account. The equivalent dose is measured in millisieverts. For most of our purposes, a milligray is going to be a millisievert, that all the radiations we deal with are approximately equal in their biological effectiveness. So these are the units that you'll see a lot, the milligray and the millisievert. The old units, which are still used a lot in the radiation safety world, are the rad and the rem. A rad is 10 milligray, a rem is 10 millisieverts, just to confuse everybody. But a rad is a unit of dose, as is a gray and a milligray. And just to orient you to the sorts of doses we're talking about here, the average background radiation dose that we get anyway, just from living, about 3 millisieverts per year. Part of that is from naturally occurring radon, part of that is from medical exposures, X-rays and so on. Again, just for orientation purposes, a mammogram produces about 1/100th of a millisievert to the breast. A CT scan produces about 10 millisieverts to the appropriate part of the body that's being scanned. So I'm just giving you these numbers just to give you a feel for the sorts of doses we're talking about. So that last slide was units of dose, and that's the amount of energy deposited in you, and that's going to be the measure of the biological damage which you're likely to have. Radioactivity, by contrast, is a measure of the amount of radioactive decays in some radioactive material, which might be suspended in the air or in a terrorist's hands. So that's a number of radioactive disintegrations per second of that particular material. And that's measured either in the Curie, interestingly enough, not named after Marie Curie at all, as I always thought, actually named after her husband, Pierre Curie. Sad, I always thought it was the only unit named after a woman, and it turns out not the case. But anyway, that got replaced with the becquerel, and a becquerel is actually 37 billion disintegrations per second. A Curie is 37 gigabecquerels. And you see Curie, the Curie unit is still used far more than the becquerel, although we're supposed to be using becquerels now. So you're going to hear much more as we go along about the biological hazards of radiation from the other speakers today. But just in the broadest of terms, you can distinguish between early effects of radiation and later effects of radiation. So the early effects, days, weeks of high doses, involves damage to the blood-forming organs or the GI organs, and Dr. Hall is going to talk about that as we go along. So these are the effects which occur over a week or two. But then we're also concerned if there is a large number of people being exposed to a small radiation dose of much later effects occurring over decades or even generations. And that's cancer risks, hereditary risks, or effects on the developing embryo and fetus. And for those of you who need to go now, here's the league table of what these risks actually are. Teratogenic risks, risks to the developing embryo and fetus, are very large. The developing embryo and fetus is extraordinarily sensitive to radiation. So they're, in the roughest of terms, 10 times larger than carcinogenic risks, which in turn are about 10 times larger than hereditary risks. So hereditary risks mean to your offspring, cancer risks refer to you yourself, the exposed individual. So, with that introduction to radiation in general, let's talk about some of the different radiation threat scenarios that we potentially might face in today's world. And there are really 4 different scenarios that you can think of. A nuclear accident, an improvised nuclear device, an attack on a nuclear power plant, or a dirty bomb. So these are the 4 real distinct scenarios that we may have to face one day. So just briefly running through those, a nuclear accident. Well, we've certainly had nuclear accidents. Chernobyl, Windscale, 3 Mile Island. We've basically had 3 moderately major accidents in the 60-year history of nuclear power. What is the risk? Well, it's the release of the fission products from the nuclear power plant. The outcome, generally speaking, is going to be long-term carcinogenesis. There probably will be very few, if any, immediate casualties. There were none at Windscale or 3 Mile Island. There were certainly a few at Chernobyl. Do people know about the Windscale accident? I was giving a talk a few weeks ago and someone put their hand up and said, what is Windscale? Yes? No? No. Interesting. Well, let me first scale these. Chernobyl was about 1,000 times larger in terms of the release than Windscale, which in turn was 1,000 times larger than 3 Mile Island in terms of the amount of radioactivity released. So Chernobyl was actually 1 million 3 Mile Islands. Windscale was an experimental reactor in the northwest of England, which caught fire in 1956. Actually, when I was 3 years old and living in the northwest of England, about 20 miles away from Windscale. Just like at Chernobyl, the government didn't fess up for quite a long time as to the nature of the Windscale accident. So I certainly drank the milk, so I keep an eye on the thyroid. Yeah, it was a very large-scale incident, and only in the 1990s did the government start releasing information about what the actual doses from Windscale were. So that's a nuclear accident, and as nuclear power increases, which it presumably will over the next decades, one assumes that there is a possibility of a nuclear accident occurring. A nuclear device is, of course, a whole different story. Now we're talking about the sort of thing which was dropped on Hiroshima and Nagasaki. So now you have 2 levels of risk. You have the immediate exposure to gamma rays and neutrons emitted from the atomic bomb, the nuclear device. And then you've got, as with an accident, you've got the fallout of the fission products. And as at Hiroshima and Nagasaki, you're probably going to get a large number of early acute deaths, most of which are not going to be radiation related, most of which are going to be blast related. And as at Hiroshima and Nagasaki, you're going to have long-term carcinogenesis issues from a large number of people who are exposed to lower doses. Likelihood, well, who knows? I've written remote here, and that's I guess my best estimate. But I mean, despite what people say, it is certainly not easy to construct a improvised nuclear device, and certainly since 9/11, it's become progressively that much harder to get hold of the radioactive materials that one might need, as we will discuss. An attack on a nuclear power plant is the third of our possible scenarios, and as you know, we have a nuclear power plant not very far from here, just north of the city. And there are really two separate scenarios that you can think of there. One is an attack on the reactor itself, and the other is an attack on the stored used fuel elements. Now, an attack on the reactor itself, as you know, a reactor is built with extremely thick walls, just by definition of a reactor. And there's always debates in the literature if a jumbo jet is flown into a reactor, will the walls hold out? I don't think we really know the answer. But nevertheless, the reactor itself is pretty well protected, and certainly again since 9/11, security is far, far better than it was. On the other hand, the stored used fuel elements is a different story. As you know, there is no repository in this country for storing used fuel elements from a nuclear power plant. So generally speaking, they're stored on site in swimming pools. There's a photo of a swimming pool next to a reactor. And here you're outside the containment area, so you don't have the thick walls of the reactor itself. Security, certainly when I visited one of these, albeit before 9/11, was poor. So a much easier target. And typically there is the same amount of radioactivity in these swimming pools as there is in the power plant itself. And for either of these scenarios, the issue is release of the fission products from such as iodine, cesium, and many others. Again, unlikely to involve too many acute deaths, but long-term carcinogenesis is the concern. And again, this is only my estimate of the likelihood. And finally, of the four scenarios, certainly the most likely and the easiest to accomplish is a dirty bomb, technically called an RDD, a radioactive dispersal device. Well, we're going to talk a lot more about this as we go along, but basically a dirty bomb is some amount of radioactive material which is blown up by a terrorist. And typically cesium, cobalt, americium are the isotopes that we may be thinking of, as we'll see. And as I alluded to when I was talking about the Goiânia story, what are we going to be faced with? Well, probably fairly small numbers of contaminated people, very large numbers of very slightly contaminated people, and very, very large numbers of concerned individuals. So psychological chaos, in many senses, is the real goal of a dirty bomb, an RDD. Outcome, well, very unlikely to result in more than a few acute deaths, risk of long-term carcinogenesis, and certainly risk of major chaos and major economic disruption. And again, of course, it's only my estimate, likelihood, likely. But we'll talk more about that as we go along. So what is a dirty bomb? Well, it's pretty simple. It's some amount of radioactive material. It's some conventional explosive, Semtex, fertilizer, whatever, some high explosive, a detonator, perhaps a time fuse. So really, other than the radioactive material, these are pretty easily available materials. Not all dirty bombs are the same. The smart terrorist is thinking about aerosolizing the radioactive material. Picture the radioactive material as a lump of metal, shall we say, which it might well be. In order to do damage, you've really got to convert that into a powder that can go off into the atmosphere. If it remains as a few big lumps, it's not going to do any serious damage. Of course, if it was in a powder form to start with, then that's a different scenario. But a terrorist has to give some thought to how to aerosolize the radioactive material. And again, we'll come to that as we go along. So let's talk a little bit about what the availability of radioactive materials might be. And this is a plot that the International Atomic Energy Agency put out every year or two on smuggling incidents. So these are incidents where radioactive materials have been intercepted at some border. So this is just presumably a fairly small snapshot of what's actually going on. And so we've got a plot here from 1993 to 2005. And there is a distinction between these purple bars here, which is fissile material, meaning materials that one might use to make an atomic bomb, an improvised nuclear device, and the orange is other material. In other words, material that's not appropriate for building a nuclear device, but certainly could be appropriate for a dirty bomb. And the trend that you see from over this decade or so is that the purple is going down and the brown is going up. So the smuggling of materials for actual nuclear devices is going down. The smuggling of materials that might potentially be used for a dirty bomb is going up. And what are the materials that are being smuggled? And again, this must be a very small snapshot of what's actually happening. These are just the intercepted events. Cesium-137 is by far the biggest, followed by americium. So one assumes that if there was a radiological terrorist event, these are actually the most likely radioactive materials to be involved. So I'll give you a few scenarios that have actually hit the newspapers over the past decade or so. In November 1995 in Moscow, a group of the Chechen rebels contacted a Russian TV station and said, go to this place in the big park in Moscow, Ismailsky Park. So they went to this place, and what do they find? They find this drum full of radioactive materials. The implication being we could have blown it up if we wanted to, but we didn't. And this was an actual constructed dirty bomb. 1998, container filled with radioactive materials attached to an explosive mine was hidden near a railway line, was found and diffused. But that is an RDD, radioactive materials attached to an explosive device. So this is a functional RDD. And this little diagram here came from a notebook that was found in a terrorist house in Herat in Afghanistan. And if you look at it, this is clearly a little diagram for how to build a dirty bomb, how to build an RDD. Yeah, so whether or not this was constructed, of course, we do not know. And just at the end of last year, this gentleman, Dhiram Barot, was sentenced to life imprisonment in London. And when he was apprehended, he had a number of notebooks, and one of them actually related to the radiation dirty bomb project. And he had a good number of notes on what he was planning. And interestingly, it was in his notes, he said it was based on an incident which he read in the newspapers in France in, I think, 1998. A truck carrying smoke detectors, carrying 900 smoke detectors, caught fire. And as you know, a smoke detector generally contains a very, very small amount of americium, a radioactive material. So this truck was carrying 900 of these and caught fire. And so he writes in his notebook, if something so small and simple as 900 burning smoke detectors could cause so much havoc, and by increasing the amount used, the possibilities are good. The radiation project, as he called it, should use about 10,000 smoke detectors, so order of magnitude larger than this French incident, and either set them alight or place them on top of an explosive device. Again quoting from his notebook here, the burning has the potential to affect around 500 people. As soon as we realized this, we concluded it deserved to be an independent project in its own right. So actually the incident in France where these 900 smoke detectors caught fire was actually simulated. So this is I don't know how well you can see this. This is a simulation of that particular event. So what we've got along this axis is distance. This is a contour plot of radiation exposure as a function of distance from the fire, from the burning truck. So we're talking about distances of kilometer, I think. But if you can see here, the doses involved are absolutely negligible. They're 10 to the minus 5 rem, 10 to the minus 6 rem. So absolutely minute doses. So there really weren't any major issues in this event in France. And even if he had managed to fulfill his project and have 10 times the amount of smoke detectors, the radiation exposure still would have been absolutely negligible. But of course, the whole story here is that the amount of panic would have been extremely large. And that's the lesson here is that when we're talking about an RDD, a dirty bomb, to an extent the size of the bomb is irrelevant. If the goal is to produce panic rather than to produce actual hazard to individuals, it doesn't really make much difference whether it's a tiny exposure like this or a very large exposure, as we're going to talk about in a few minutes. The amount of panic is probably going to be pretty well dose independent. So Barrow was not being foolish, really, when he wanted to build a dirty bomb out of this very small amount of radioactive material. But there are certainly radioactive materials fairly easily available in this country. Here's an example of many you can see and find in the literature. In North Carolina, these tubes of cesium, you can see the scale here. This is a quarter, dime? Sorry. Okay, sure it is. Yeah, so you see how small these things are. So these are fairly high activity sources that are used for radiotherapy. They were taken from a locked safe in a hospital and never recovered. And here's an accidental finding. So here's a steel mill in North Carolina, and the big crushers had a Geiger counter. Interestingly, just before they crushed the material, and sure enough, the Geiger counter went off, and they found a 2 Curie, which is pretty big, cesium gauge found on the scrap metal conveyor belt just before it was about to be squished. It was traced back to a batch of 4, which belonged to a Baltimore chemical company. 3 have now been located, one is not. And even more common, moisture density gauges. These radioactive devices are used routinely. When you build a road, you want to know how much moisture there is in the tarmac. You need to get the right amount. So there are 20,000 of these in use at the moment in the US, and about 50 of them per year are reported missing. And certainly used to be the case they were always reported on the internet, no longer I think, but here's a missing device report for one of these things. So there's a lot of these devices around. But again, I'm only picking very specific examples to indicate to you it's not that hard to get hold of relatively small amounts of radioactive material, should you want to. So, you could... What might happen if you actually blew up some of this radioactive material? Well, you can make arbitrary distinctions between a small dirty bomb and a large dirty bomb, and the small and large depends really on how much radioactive material is being exploded. And as I say, although the doses are going to be very different depending on what sort of RDD it is, the amount of chaos may well not be very different between any of these. The amount of chaos may be actually quite similar. And yeah, let me just take a moment to talk about the New York City urban dispersion program. If you want to try and figure out what the effects of a dirty bomb might be, you better have some capability for actually predicting what the effects of wind are going to be, and the environment and the tall buildings. So you really need good models to be able to predict the effects of a given dirty bomb. And this program was really designed to test models of how well one can predict the dispersion of some material. So what they did in this 2005 field test is they released some benign gas, which I think you can just see a little bit of it here, actually outside Madison Square Garden, outside Penn Station. And then they had detectors placed all over the city, and the idea was, well, can we predict what was detected in all these different detectors? So here's where the simulation was initiated outside Penn Station here, and they had detectors all over the place. And the idea was, well, let's model what goes on and see whether we can't get some good agreement between our measurements and our models. So there is Madison Square Garden, and there's where the release took place. So here is a simulation. And you see the time scale here, pretty quick. So the whole dispersal, yeah, they didn't bother simulating up where we are. They're only interested in downtown, of course. But, so this is 30 minutes, 35 minutes. So by this time, all the dispersal is basically done. This is a log scale, so green is many, many orders of magnitude down from the initial concentration. So the story here is that it's all going to be over in a few minutes. The radioactive material that's sitting on the ground will already be on the ground. The radioactive material that's fallen upon you will already have fallen upon you. Here's another simulation, this one in Los Angeles. Again, look at the doses here. This is a big dirty bomb. This is the large RDD. This is actually the same amount of material that was in the Goiânia incident that we started from. So it's a 1,000 or a little over 1,000 Curies of cesium-137 blown up with 5 pounds of high explosive. And the assumption here is it was completely aerosolized, so it all goes into the atmosphere. This, of course, was the way the wind was blowing, and the scale here is 6 kilometers by 6 kilometers. But you see that the doses are actually small. In this small region here, 1 rem. In this larger region here, 0.01 rem, which is a very small radiation dose. So even with this large RDD, the doses are going to be generally small. And just one further example, about to say slightly closer to home, slightly close to my home, I guess. The Olympic Stadium sports complex in Athens, here it is, that's the Olympic Stadium. Home just a couple of weeks ago to the Champions League football final, Liverpool against AC Milan. And you see this guy here, but he's looking a bit concerned as he's walking to the ground. Yeah, that was me. So what would happen if there had been a dirty bomb in this scenario with 50,000, 70,000 people in the ground? Well, we have the tools to simulate that. So here's a simulation of what might happen. I don't know how visible that is, but there are some dose contour maps here. So this is 200 meters, and this is the 1 rem dose line. This red line here is 25 rem. And this is a 24-hour exposure dose, meaning this is presuming that nobody moves for 24 hours, which of course is not a realistic simulation. So the doses are actually going to be, would actually be significantly less than that. But this is a large dirty bomb, 5,000 Curies and 10 kilograms of high explosive. But we can actually, so in this case, the dirty bomb was exploded in this simulation on the other side of this railway, on the subway line, or metro line, so just about 200 meters from the stadium. So let's look locally what might happen just in the vicinity of where the explosion took place. And now you can see rather higher doses. So we got up to 300 rem here. But look at the distances involved. We're only talking about some tens of meters here. So only people very, very close to the explosion are going to get high doses. Everybody else, even in a large RDD scenario, are going to get low doses. Okay, we're going to hear much more this afternoon about healthcare provider response to a radiological event. But again, let me just stress in this overview talk that almost everybody that's going to present at an emergency room, a clinic, is not going to require treatment. And again, just relating back to the Goiânia scenario, that this huge number of people showed up for screening, but a very small number of people actually needed any treatment. So we have a very big triage issue. So, which brings us back to actually our own program here at Columbia, that the hypothesis, the premise is that after a radiological event, small or large, in a big city, we're going to need to screen large numbers of people within a few days. Both, well, for two reasons. I mean, both because of the need for triage. Obviously, no hospital or no city hospital can deal with 100,000 people being admitted. So you're going to need triage. But also because it's very clear that active reassurance measures are a good antidote to reducing mass panic. I mean, what I think is well known doesn't work is if somebody like me in a white coat goes on the TV and says, "Don't panic, it's okay." That doesn't work. That's not a good way of reducing mass panic. But, yeah, I caught this from the New York Times last year. A frenzy can fade if the public believes the government is being honest. So if there's some active way of showing large numbers of people that they really are not significantly exposed, then that is a way of defeating the terrorist goal of producing mass panic. So that is the rationale for our center here at Columbia for high-throughput, minimally invasive radiation biodosimetry. Well, I say Columbia, but you see there's a large number of players. And one of the things we're trying to do is to provide fully automated, ultra-high-speed workstations based on a finger stick of blood, which is something you can get very quickly, unlike getting blood from the arm, which takes forever. No human intervention. If you can use a drop of blood from a finger stick, like a diabetic gets, you can get that very quickly. Or if you can use saliva, for example, or sweat, or even perhaps urine. These are things you can get very, very quickly, and so you can potentially get high throughput. And beyond that, you have to automate everything. You can't, if you're going to be dealing with 100,000 samples, you can't be doing it manually. And there are various different biological endpoints that you can think of for biodosimetry. The classic one is the micronucleus assay. The downside of that is that it takes a long time to process. It takes 3 days to process. You can still get the throughput, but you don't get the answer for 3 days, which is not really what you want in the case of if you're trying to avoid the mass panic. There's a more modern technique called the gamma H2AX assay, which does give same-day processing, same-day result. Its downside is the signal only lasts for about a day and a half, so you have to get your samples in a day and a half. So there are pluses and minuses to these two different approaches. And the concept of use is that the first 36 hours, you would actually use this assay, which gives you same-day processing. After that, you'd have to go for the slower technique. So will it happen? I promised you I'd talk about that, and the answer is probably yes. This is a quote from the former UN Secretary General, Kofi Annan. Many experts tell us the question is not whether, but how soon. We will see, for example, a dirty bomb detonation in central London or some other major capital. And I think this realistically, this must be the case, because it really is not that hard to do. To make a large dirty bomb, the type that I was doing the simulations of, that's not easy. To get hold of 1,000 curies of radioactive material is certainly not a trivial thing to do, and all the authorities are working very hard to limit access to these large radioactive sources, and I think are starting to do a pretty good job. The issue, I think, is more the smaller radioactive sources, which are still pretty easy to come by, and although the biological hazards will be a lot less good, the level of panic and the level of economic disruption may be just the same. So the bottom line is that in the event of any sort of radiological event, you need to get a good team together, and meaning that that team has to be prepared beforehand. You need healthcare providers, you need physicists, and most important, you certainly need communicators. So any large facility needs to have in advance as part of their disaster plan, something for a radiological event. And this is an interesting survey done, it's 2002, American Hospital Association. 46% of hospitals, half of all the hospitals surveyed, did not have radiological terrorism in their disaster plan at all in 2002. I wonder what it would be today. If I was a betting man, I would say it'd be a little more than this, but not that much more than this. Where should you go to get more information? Well, go to CDC or OSHA. They have tremendously good websites, and these are the URLs, but I'm sure if you type CDC into Google or dirty bomb into Google, you'll find these. The American College of Radiology and Astro have actually produced a very good document, I think the best that I've seen, called Disaster Preparedness for the Radiology Professionals, but it's actually relevant to all healthcare professionals, not just radiology professionals. That's a link there. And the NCRP, the National Council for Radiological Protection, has got a pretty good book with a lot more detail, of course. So let me end and say, well, my real bottom line is the threat of radiological terror is very real. Most scenarios that I think are realistic scenarios present as much organizational challenges as anything else. And that's our bottom line, and that's why we're here today. And I'll thank you, and we have time for some questions.